in space. Okay, that was a really bad joke, but I just still think this is pretty cool. There's something about recursion that I really like, okay? But anyway, okay, so today, hopefully, I heard one minor criticism, which was that the audio quality wasn't so good. So I'll try to speak louder, and I'll try to get a microphone and figure that out. I apologize for people in the room who feel like I'm blasting them with my voice. So I don't think, one other issue is that homework. So I gave it like about 10 seconds worth of thought before class started. I decided, yes, I'm going to have everybody hand in the homework, okay? Now, for the people that are off campus, there might be special cases, and I know of at least one special case, which I'll handle differently, okay? So don't panic if you fall into the special case, okay? But the reason I'm going to have you hand in the homework is, first of all, I might choose to have like a TA check off that you've done them or something like that, okay? But the other reason is that, the main reason is because if I don't have a discrete point in time where you'll feel some level of guilt, then you might not do anything. So in order to get the ball rolling, I think it's important that you hand them in. Now what I suggest that you do is, for the off-campus people, I'll send information about how you can email the homework to an email address. We have actually I have a Gmail account to use for that purposes. For the on-campus students, if you want to hand it in physically, that's fine. And then what you should do is photocopy it. So hand in the photocopy, okay? You don't have to hand in the photocopy. If you want to hand in the original, it's fine. But if you come back later and you say, I don't have the original to study from, okay, I'm warning you now, okay? Because I don't know when they'll get returned, maybe never, okay? So don't hand in your original, okay? Hand in your photocopy. And for the off-campus students, you're going to scan it, and you can either email it, well, you can email it, or you can email a link through FileLocker, I guess, if you really want to. Either is fine with me. So, if you feel so inclined. Okay, but I need to have a point. Now, the first homework I just checked is the first 5 problems of Chapter 1, and I think they're relatively straightforward problems, so it shouldn't be too onerous. You should try to get those done for Friday, okay? You don't have to email me for homework extensions. Well, if you want to email me for homework extensions, that's fine. Then I'll just reply and say yes, okay? But if you put off the homework and you get behind, then that's going to hurt you, okay? Not because I'm going to grade against you, okay? And this is sort of like hard for students sometimes to get used to, because they're used to like someone having a hammer and some kind of onerous thing happening, and then being chastised. So I'm not going to chastise you. I guess if somebody really falls behind and eventually you have a TA and somebody checks and it seems like you haven't done anything, I might come up to you and say, you haven't done anything. That might not be a good thing, okay? But what's going to happen is if you don't do the homework, you won't be prepared for the exams. Why? Because the exams are going to be not just based on the homework. I'm basically going to just take homework problems and put them on the exam. Okay? I may choose to do something else. I always leave that open as a possibility, but that's my plan. Okay? So if you don't do the homework, you don't know how to solve the exam problem, pretty much by definition. Okay? Now, the other thing that I'm going to tell you, which I told you last time, is I like having a bunch of versions of this. These are the notes for the class. At least one person emailed me that they couldn't find the notes. I'll quickly go over real quickly where they are again. Was everybody able to find the notes? They're on the notes webpage. They're the first link. It's like one link that has like 200 pages of notes, okay? So you may not want to print the whole thing. Just print out little sections of it. It's up to you, wherever you choose. But it's all there, okay? Now, here's the special secret to the course. You're supposed to read these. Okay? I'm not kidding. Okay? This isn't a joke. I really mean it. Okay? So, for instance, in the first lecture here, it says here, okay, so the first lecture was introduction, and the second lecture is chapter 2.1. So over here on chapter 2.1, okay, so there's chapter 2, and this is chapter 2.1. Okay. Okay. So here, this is chapter 2.1. There's page 1, page 2, page 3, page 4, page 5. There's 6 pages. So you have to read these 6 pages. How many people read these 6 pages before class today? Hold your hands up high and be proud of your accomplishment. Okay? 4 people, okay? Okay. How many people did not read these 6 pages? Okay. So, I mean, this kind of takes you in numbers, and then you feel like you screwed up, but there's a lot of other people who screwed up too, so you don't screw up. Okay. Did you read them?
I did 3.
Okay. Okay, we'll count you in the plus category. Okay, so, what are you going to do after class? You're going to read these, right? Plus, you're going to read the section for Friday, right? Which is going to be 4 pages. Now, what I try to do is write these in a way that is pretty easy reading, so it shouldn't be too onerous. Now, they're jam-packed with concepts, though, so you might find that you have to read some sections of them very slowly. So I really expect you to read this and understand it, okay? Why? Because my expectation is that you actually read this and understand it before you get to class, and then in class we're just going to talk about it, right? So I'm not going to teach this to you in class because it's hopeless. I can't possibly teach you to do this in class. It's way too much material and it's way too fine-grained. You have to go and look at it and study it before class, and then we're going to just talk about it to reinforce it and answer your questions, okay? So everybody, what are you going to do? What's the most important thing to do before every class? Read the notes. I want everybody to repeat that. Okay, this is sort of like this physical process of doing something to really fully drive it into your consciousness. I want everybody to say, okay, I'm going to put your hands up. I pledge as a good student of Purdue University to read the notes. Okay, so repeat after me. I will read, everybody say read. I will read the notes. I will read the notes.
Yeah.
Okay, thank you. Okay. I'm very proud of you all for taking this important step forward, okay? So it's very important because I know that usually you don't. I mean, you're a human being and I didn't, but you're going to have to, because if you don't, you won't know what I'm talking about, okay? And you won't be able to do the homework problems. And there are homework problems due this Friday, okay? Okay, so this personal responsibility bit is going to be a big deal in this class, because if you don't do it, you just won't follow it, okay? Okay, now what I'm going to do is I'm going to start talking about the material. Oh, by the way, and are there any questions about the content of this course? So the basic philosophy of this course is that we're going to use model-based methods. We're going to solve inverse problems. This is going to be a key issue in the course. Because many problems, like in imaging, are really inverse problems. When you want to find out something you can't directly observe. So there's the so-called, Professor Bell actually invented what is called what's his name? The Mick-Jagger's theorem, okay? Okay? Mick-Jagger's theorem states that you can't always get what you want, but if you try sometimes, you get what you need, okay? And that's really the core of this class. You don't always have what you want, okay? But you may have what you need. So you take what you have, okay, and you try to get what you want, okay? So that's solving this inverse problem of finding what you want from what you have. Now, okay, so that's a simple concept in pairs, but it has a lot of complex implications. So when we solve these inverse problems, one of the key things we're going to do in this class, not the only thing, but we're going to figure out a statistical framework, you might say, a probabilistic framework for solving these inverse problems, okay? And so in order to do that, and probability is essential. See, the problem is if you don't have probability, then you can get all kinds of ridiculous answers to questions, okay? So, for instance, if you have a low-pass filter that has a frequency response of a Gaussian, okay, I'll move this, hold on, because I'm going to draw something on the blackboard. If you have a low-pass filter in frequency, which has a response of a Gaussian, it looks like this, right? Okay, now, there's a lot of attenuation at the high frequencies, and then there's not so much attenuation at low frequencies, right? So this is like a low-pass filter. In theory, you can always, mathematically, you can invert this. You just divide the frequency response of the signal by this function. In practice, you can't. If you have a low-pass filtered signal, okay, you can't recover the signal out of band in a practical sense. Why? Because if you try to divide by in theory, you could just take the low-pass filtered signal, take its Fourier transform, you could divide by the frequency response and recover the original signal. But in practice, the attenuation might be huge. The stop band of this filter could have a stop band rejection of 300 dB, okay? 300 dB is, or I don't even, what it's 10 to, 300 dB would be 10 to the minus 30, right? In amplitude, right? So it would be 10 to the minus 30. Well, I mean, good luck. Try to remove a gain of 10 to the minus 30. Any small amount of distortion or noise is going to completely destroy your result, right? So in practice, yeah, mathematically you can recover it, but in practice you can't recover it. So how do you capture that idea that it's not practical to do that? You need probability, because you have to be able to describe the fact that the signal's not perfect, that it's not really deterministic, it's statistical, okay? So probability is going to be absolutely essential to what we do in this class, and that's why a large amount of what we're going to do is developing stochastic models. But not just any stochastic models that are good for describing real images and real data and real signals, okay? So when you look at the themes of the class are going to be solving inverse problems. A key aspect of solving inverse problems is optimization, so we'll spend a lot of time on optimization. Well, another key aspect is going to be stochastic modeling, because we need statistical models for data in order to be able to process them, okay? And that's why we'll spend a lot of time on probability. So, your graduate students, you don't need as much motivation as undergraduates, but you still need motivation. And furthermore, I should say one more time that the course doesn't really emphasize a lot of real applications, but you need to take my word for it a little bit, that there are a lot of applications that use this. And if you look at proceedings for a lot of conferences these days, in Signal Processing Society for sure, but even in other societies, applications-oriented societies, okay? Societies that do various kinds of imaging, electron microscopy, material science people, biology, all kinds of things, medical imaging, they use these techniques. So becoming conversant in the language and techniques of this field will really help you be able to read the literature, okay? But I won't be talking so much about applications because, frankly, there's not enough time. If I really want to go through all the theory and understand the underpinnings of these techniques, then I can't spend a lot of time on the individual applications, okay? But hopefully still, that even though the course is mostly talking about theoretical techniques, I think it's quite relevant to applications, okay? Okay, so that's a little bit of more background on motivation. And with that, I'm going to launch into this first chapter, which really talks about probability, okay? But now you know, and some of you probably have had probability, but we're going to cover it, we're going to kind of blaze through it very quickly now. I spent a lot of time, hold on, how come the document camera didn't turn on? Did I do something wrong? The document camera's on. I switched the source. Let me try. Let me see if the PC works. That's sort of not good. Touch to sensing screen. Does that help? Oh, there it goes. Okay. Okay, it's just slow. Okay. So I spent a lot of time trying to rate this chapter on probability estimation, and random processes, so that it's easy to understand that it doesn't say anything that's really false, and that it captures the essence of the ideas. And a lot of people in this class I know are going to have different kind of background. If you don't have a strong probability background, I recommend you try to read this very carefully, and you try to read it more than once, because it's hitting a lot of really important big ideas kind of quickly. Let's see if we can zoom in a little bit, okay? Okay, so first, let's see. So we have a thing called a random variable, okay? A random variable x. So x is a random variable. In fact, the definition of a random variable is pretty complex. It's really a function. If this confuses you, don't worry about it too much. But it's a function which maps from a probability space. So omega here is a member of a probability of a space. It's a mapping to the real line. Okay. So it's a function. So a random variable is really a function. Okay. But I think the way people conventionally think about it is, as a random variable, is the outcome of some random experiment. That's the way people usually think about it, okay? It's not, in order to be able to really mathematically make things rigorous, you have to think about it in this more precise way, okay? But, so basically, the bottom line comes down to, if x is a random variable, its distribution is going to be specified by what's called the cumulative distribution function. So the cumulative distribution function, the CDF, is defined as the function f of t, which is equal to the probability that the random variable x, say, is less than or equal to some value t. So t here is just a regular variable, and x is a random variable. Random variables and regular variables are not the same thing, because random variables are actually functions which map from a probability space to the real line. If that confuses you, don't worry about it. But the key issue is that random variables and real variables are different things, okay? So this is a plain old function, and it has some property which is, well, if I increase t, then this function has to be increased, so that if you have t is greater than, say, t1 is greater than, say, t2, then it must be the case that f of t is greater than or equal to, or f of t1 is greater than or equal to f of t2, right? So it has to be a monotone increasing function, but it doesn't have to be strictly increasing, because it might be that, say, x, between t1 and t2, the probability of x falling in that range is 0, so that these values are equal, okay? Now, furthermore, it's the limit as t goes to infinity of f of t is equal to 1, and the limit as t goes to minus infinity of f of t equals 0. That's to say the random variable has to fall somewhere on the real line. And it's going to be, I think it's, what is it? It's left-hand continuous. It must be right-hand continuous. So you can read the notes, but it's right-hand continuous. That's to say, if it has any jumps, cumulative distribution functions generally look like this. They kind of, if they start at 0 and they kind of go up, and then if there's a discrete probability that you take a particular value, then the it has to be right-hand continuous, right? So the problem, so then it won't take on the value here, and it will take the value on there. So it looks like, it should be strictly increasing. Okay. So you have dump discontinuities. They could have dump discontinuities in it, but it'll be right-hand continuous at the points of dump discontinuities. And it can only have a countable number of jump discontinuities. Why? Because there are only a countable number of open intervals on the real line. So, okay, that means anything to you. Okay, so now what really happens though is for most people, and okay, so I don't want to say anything that's wrong in this class, okay? But on the other hand, we don't generally need all the machinery of probability to do everything we're going to do in this class. So, if you're interested, and if you're really into this stuff, you should be interested. You should take a course where you learn about measured theoretic probability that I'm not going to go into, and you learn about Lebesgue integration and all that good stuff. For that, you need some real analysis and so forth. But I'm going to sort of skip to, with that, hopefully without saying anything that's really wrong, I'm going to try to skip to sort of what you really need, okay? Which is that usually we deal with the probability density, which is that we differentiate cumulative distribution function, okay? And we get what's called a density. And then the hope is that, well, the probability that the random variable falls in some interval, right? So say between t1, so if it's less than or equal to t1 and less than or equal to t2, is going to be equal to the integral between t1 and t2 of the probability density. Now, it's not necessarily the case that's true, okay? We'd like this to always be true, and for this class we can mostly always assume it's true, but it's important, I feel some intellectual responsibility to point out that it's not always true, okay? Okay, so now it's not always true for two reasons. The first reason seems like just a detail, but the second reason isn't a detail. It's just, it's just not true, okay? So it's not always the case, this is not always true. So it's not always the case that f of t is equal to the integral from minus infinity to t of t of tau d tau. There isn't always a density function, is one way of putting it. You don't always have the luxury of having a density function. Okay, so there's two reasons why you might not have a density function. The first reason is that, well, it might be that the random variable is discrete. So it only takes on particular values. So let's say, so one possibility is that, it's 0 and then all of a sudden it jumps, right? And then say it jumps again. And this is 1. Right, so it starts at 0 and it goes to 1, okay? And so in that case, there's no probability density because I can differentiate the thing, but the derivative doesn't exist here, right? So the derivative is 0 everywhere except for just 2 points, and when I integrate that, I get 0. And you say, oh, you're splitting hairs, come on, cut me a break, we're all engineers, we know about delta functions, you're playing games with us. Well, then what I could just do for the probability, so this is f of t, and then the probability then would be p of t. I could just put two impulses at those two discrete points, right? And make each impulse 1/2. And I say, well, hold on for a second, you can't do that because that's not a real function, okay? And you go, oh yeah, come on, cut me a break. This is an engineering course, it's real enough, okay? And then I would integrate this, and then I have a legitimate probability density function, okay? But in fact, I have to tell you, it's much worse than that, because there's a thing which I just can't help but explain because it's too much fun, okay? Is that there's a thing called a Cantor function, okay? So what you do is this. You take the interval from 1/3 to 2/3. So you take 1/3 of the real line, right? And you make the function 1/2 in between there, okay? And then you start off at 0, so this is a function which goes from 0 to 1. So you start at 0 and you're going to end at 1, okay? And then the middle third you take to be 1/2, okay? Then you take the remaining interval where you haven't defined the function, and you make the middle third of those two intervals both not 1/2, but 1/4 and 3/4, right? And you keep repeating that recursively, okay? And you add that to infinity, okay? Now what you do is, you can say, well, now what you have is a bunch of discontinuities. But in fact, you increase to infinity and you show that the function is basically not discontinuous. okay? I mean, you have to fill in a little bit. You have to, there's going to be some points where you'll never get any value, okay? So, asymptotically. So what you have to do is just extend the function to its continuous limit. So, here's the disturbing idea. This function is a continuous function which goes from 0 to 1, right? Its derivative is 0 almost everywhere, okay? So this function's derivative is 0. It goes from 0 to 1, so its integral, it's not discontinuous, so there's no impulses in its derivative. But I integrate the derivative and I get 0. I mean, I always like to give the analogy of this. I mean, maybe it's a bad analogy, but I can't stop myself, I'm sorry. That when I was a little kid, we used to play this game called green light, red light, green light. Does anybody ever play that anymore? Okay, so what you would do is you look away from your friends, and they would stand over here. And you'd look away from them, and you'd say, green light, and then they'd try to run, and then you'd turn around real fast and say, red light, okay? As you see them moving, you throw them out, okay? So they try to get from 0 to 1, okay, without you seeing them, okay? So what happens is the Cantor function gets from 0 to 1, it sort of cheats. Somehow when you're not looking, it sort of jumps ahead, but it doesn't seem like it should be possible, but it does. It sort of fits all its changes into a set of points that are uncountably infinite and you never see. And you get from 0 to 1, so this basically blows your theory that probability cumulative distribution functions always have to have density. So there are not always densities. So you can't always assume there's a density. But now that I feel like, now we've purified ourselves by realizing that, here's the counterexample, the world is a bad place, now we're going to forget it, We'll never visit that issue again. Because we'll never consider any of those bad situations again. So there are bad functions out there, but we'll ignore them. Actually, they get a lot worse than that. That's among bad functions, those are good ones. So, now, there's also a thing called the Lebesgue-Stieltjes integral. That's basically a variation on or there's a thing called a Riemann-Stieltjes integral. You probably forget it. But basically, what happens is that you can compute the expectation of a random variable x, right, by actually computing the Stieltjes integral. So you go from minus infinity to infinity, right? We'll put here tau df of tau, okay? So you don't need the density function to compute the expectation. You can compute it from the cumulative distribution function, but you just have to use a Stieltjes integral. And if it's a really messed up cumulative distribution function, you have to use the Lebesgue-Stieltjes integral. Actually, maybe you never have to use it. Maybe the Riemann-Stieltjes integral always works. I'm not sure, I know the Lebesgue-Stieltjes integral has to work, Now, if you forgot what the Stieltjes integral is, you actually learned it, but it was like you took the test and you forgot it, But if you go back in your calculus book, I'm sure it's in there. You learned it at one point. And it's just a small variation, But it's useful. Now, expectation is very fundamental for random variables, and we'll use it a lot. It's actually more fundamental than probability density function. The expectation really can be used to define the properties of probability. Density functions don't always work, But, so I want to talk a little bit about expectation. First of all, expectation is linear. So the expected value of x and y is equal to the expected value of x plus the expected value of y. In general, the expectation always exists for any positive random variable as long as you allow infinity as a possibility. The only time you run into problems with the expectation is that if the distribution of random variables is such that its positive part has infinite expectation and its negative part has negative infinite expectation, then you have a problem because what do you do when you have positive infinity minus positive infinity? Or you have positive infinity plus negative infinity. Is it zero? What is it? So it's not defined in that case. But whenever, for any positive random variable, the expectation is defined. And in general, for any random variable where the expectation of the absolute value is finite, then the random variable expectation is defined. So the expectation is defined under very general conditions, okay? Let's see. Oh, now what happens is that, okay, this is like, this particular lecture has a lot of this stuff where I have to say things in order to, like, clear my guilt, okay? That you might not use, but I just feel like I have to say them so that I haven't said something that's wrong, okay? But I want to point out that, okay, now you can have this thing called a random process, right? So you can have a sequence of random variables. You can have a finite sequence of random variables, you can have an infinite sequence of random variables. So if you have a finite sequence of random variables, you can have x1, x2, right, x3, to xn, right? Now, if you have a finite sequence of random variables and you want to define the distribution of this finite sequence, now what you have to do is you need to have a multivariate probability, a cumulative probability distribution function, or a multivariate density, right? So what you have is you have like f of t1, t2, all the way through tn, right? And that's the probability that x1 is less than or equal to t1 through xn is less than or equal to tn. Okay? So, and if these are not independent random variables, then, you know, these questions can't be asked independently, right? There's joint distributional information involved here. And then you can differentiate all this, right? So you can get a density function. Let me see. So you get a density function which the t, say 1 through tn, is basically the derivative of this thing with respect to all the variables, t1 through tn of f of t1 through tn. So you can look at the notes for detail. And what I write in the notes is precisely true. So the density function, it doesn't always exist, the multivariate density function. But for all the cases we're going to consider in class, it mostly tends to exist unless the random variables are discrete. Okay? So, okay, now, if sometimes what will happen is the cumulative distribution function has the property that, of the multivariate distribution, has the property that it's the, it can be written as the product of a bunch of functions, one for each variable. So it might be the case that the cumulative distribution function, the joint cumulative distribution function for the random variables, is the product of the individual distribution function for each random variable. If that's the case, then we say that the random variables are independent. Okay? But it's not the case that random variables are always independent. Usually they're not just independent, but they might be independent. Actually, independence is a pretty commonly made assumption that allows you to be able to get answers to problems, okay? But oh, by the way, they're not just independent, they're actually jointly independent. And I think there's a problem in the homework on this. So one thing that's kind of interesting is, okay, so let's say you have a bunch of random variables, okay? So you have, x1 through xn, right? And now somebody comes along and they say, okay, for all I and j, xi is going to be independent of xj as long as I is not equal to j. Obviously, if I isn't equal to j, then xi is not independent of itself. Okay? So you have so you have a set of random variables that are pairwise independent. Okay? So now, if they're pairwise independent, are they jointly independent? No. Okay. So, I mean, if you know me at all as a person, as a teacher, you know that the answer has to be no. Okay? Because I wouldn't ask you a question like that unless I was trying to trip you up. Okay? Because, so you know me as a teacher. You know the answer is no. Okay? They can be pairwise independent, but that does not necessarily imply joint independence. Okay? I use that upside down pi symbol as an indicator of independence. Okay? And so, of course, then the first question you ask is, well, give me an example. I mean, okay, so here's an example. Does anybody have a coin? Actually, this is a good example you can do with the document projector, because I would have a coin except for I've stopped, oh thank you. I've stopped using currency, like physical currency. I'm now transitioned into the electronic age, okay? So what I do is this. I have two random variables. The first random variable is equal to, say, x1, okay, is going to be either plus or minus 1, right? And x2 is going to be plus or minus 1. And I'll pick the plus or minus 1 as the outcome of a coin flip. So if it's heads, it's plus 1, and if it's tails, it's minus 1, right? And so I'll flip the coin twice. Oh, I missed. Okay, that's heads, okay? So the first one is plus 1. And I flip the coin again, okay? And oh, I got heads again, so that's plus 1 again, okay? So the two random variables are the outcome of two independent coin flips, right? Now, x3, I make equal to x1 times x2. Okay? So that will also be either plus or minus 1. Now, it's easy enough to show, and I think it's actually quite intuitive, that x1 and x3 have to be independent. Because x3 is x1 flipped a second time randomly by an independent event. And by the same logic, x2 and x3 have to be independent. And clearly x1 and x2 are independent. So they're all three independent. But if I know x1 and x2, I know x3. So clearly this is an example of three random variables which are pairwise independent but jointly dependent. I just like that example because, you know, I don't know that it's very useful, but it's just good to know because otherwise I for a long time thought that any pairwise independent random variables must be jointly independent, and I was shocked to find out that was not the case. So it's better to find out these things early in life. Let's see. Okay. Now, one of the things that is really, really fundamental to probability and signal processing, okay, is conditional expectation and conditional probability. So you have two random variables, x and y, right? So they're not necessarily independent random variables. They have some sort of joint distribution, right? And this is one of the, I mean, it's really kind of interesting. There's massive misunderstanding of probability in the real world, okay? And, you know, in fact, all you have to do is read the newspaper to see all kinds of idiotic things that show people don't understand probability. And furthermore, without being specific, so I don't offend anybody, there's lots of communities of people who use probability that don't understand it, and they do really weird things with it. And some of the weird things are useful, so I shouldn't pick on them too much. But the stuff is, like, wrong, okay? So now, one of the places where people really just don't understand probability at all, for the most, a lot of people just really don't understand probability at all, is expectation, conditional expectation. Conditional expectation is very subtle, and it's very fundamental. And I actually can't give you a really precise definition of it here because it gets too complicated. It goes beyond the scope of the course. But I was very careful to write the notes that you're going to read very, very, very carefully, okay, so that they're actually not false. There's nothing in the notes, as far as I know, that is untrue. It's just very coy and slick and careful to quite not ever lie, but try to convey the truth and never say anything was wrong, okay? So if you read it very carefully and you believe it, hopefully you won't believe anything that's false, okay? Now, but that said, the actual machinery of conditional expectation is a lot more complicated. So basically, I'm not even going to try to explain it because it gets too complicated. And one of the issues here is this. If you have the conditional expectation of x given y, right? Okay, is this, so first of all, you have the expectation of x. Right? And then you have x. Okay? Is x a random variable? Yes, obviously, right? Okay, I define it as a random variable. Is the conditional expectation of x a random variable? No, it's just a number, okay? It's just the expectation of x. It's like 3 or pi or e or even minus 6 or something like that, right? Is the conditional expectation of x given y a random variable? Yes. Yes, that's a random variable. And the way to think of it is it's a function of y, because for each particular value of the random variable y, it's a different number. So it's any function of a random variable. If I take any function of a random variable, that must be another random variable, okay? Okay, that's a really like canon law, okay? So you're going to read the notes because this gets too complicated for me to go through, okay? But that's a really important idea, and just read the notes on conditional probability because I'm not even going to try to explain it. It'll just really get confusing. Okay. But basically, I think the key issue with conditional probability is this. The conditional probability is a random variable, and it's not unique. That's what makes it complicated to define. Because there's really an infinite number of different random variables which all could have the same probability. They can just vary in small ways where the probability of being different is zero, okay? So therefore, it's really defined as an equivalence class of functions which all have the same behavior. But as a practical matter for our class, yes, the way you'll really do this is you'll compute a probability density, a conditional probability density x given y, right? And if you want to compute something like the conditional expectation, you'll compute that the conditional expectation of x given y, given y equals little y, is going to be the function given by the integral of x times p of x given y dx, okay, from minus infinity to infinity. This will be a function we'll call f of y, and then the actual conditional expectation, x given y, will be just this function evaluated with an input of the random variable y. I know that was a little bit confusing, and maybe I should have written this over in a different section, but it is what it is. Read the notes carefully, okay? Because I just, and if you want to go off, you can actually study this independently. It's worth understanding, but you need to know a little bit of Lebesgue integration. Okay, now, I also want to point out something else, which is that the probability that some random variable takes on a value in subset A, right, can always be expressed as you can take a function IA, okay, as of x, right? So this is this is a so-called indicator function. So if the variable here is x, so this is equal to 1 if x is in A, and it's equal to 0 if x is not in A. This is an indicator function, right? And then what you do is you say, okay, I'll take the expectation of this indicator function of x. So that's a trick that comes up and is useful. So it's one way of thinking about probability. Okay, expectation and probability can interchangeably be used as the basic power tool for talking about probability. Okay, and now this is really important. I want to spend a little bit of time on it. I don't have too much time, so I'll focus on it the rest of the thing. Is that we have the so-called filtration property. Okay, so the if you have the expected value of x given y, okay, and you take the expected value of that, right? What's that equal to? So if you have the conditional expectation of x given y, and you take the expectation of that, what do you think that's equal to?
A number.
Well, that's a number, and particularly what number is it? It's just the expected value of x. So that's a pretty handy tool, because what happens is sometimes if you want to calculate the expected value of x, it's easier to assume something's true first, and then take the expectation over that thing that you assume is true, right? So like, for instance, you want to say, the expected happiness of a Purdue student. So you say, well, calculate the expected happiness on an exam day, and then the expected happiness on a regular day, and then take the expected probability that it's going to be an exam day, okay? So that's often an easy way to do it, okay? Now, there's another thing, which is that if I have, what's the expected value of x given x and y? Okay. it's this X, and I like to call this, and I'm sorry for repeating myself for those who have heard it before, because you probably know what I'm about to say. I call this what's in a jar of peanut butter, okay? So, okay, for those of you who know the answer to this question, don't remain silent, okay? Okay, what's in a jar of peanut butter? Yes?
Peanut butter.
My gosh, you're a genius! Peanut butter is in a jar of peanut butter, okay? If I ask you what's the expected value of X given X and Y, the answer is X. I know what the answer is because I've been given it, okay? Okay? So, now we have this filtration property, which is that, okay, so I have properties which are a little more complicated here, a little more general. If you take the expectation of the conditional expectation of X given Y and Z, and you condition that on Y, okay, then it's going to, that overall thing is the conditional expectation of Y given Z. So basically, you get rid of the Z, okay? But it's really just a generalization of what I've just explained here, okay? And yeah, if you have an expectation of a function of X, right? We'll zoom in on this. If you have an expectation of a function of X times Z, condition of X and Y, well, I know X, so I know it's in the jar of peanut butter. So I know it. So f of X here is a constant. I can take it out of the expectation, right? And I get this. So whenever you're conditioning on something, and you're taking the expectation and you're conditioning on something, and that part of that expectation is the thing you know, you can, that's effectively like a constant, you can take it out of the expectation. Because the expectation is linear, you can always take it a constant out, right? So this turns out to be very useful, and the thing that's important to know is that unlike the stuff you had in undergraduate probability where you took density functions and you did integral, those things with density functions are not always true. First of all, the density functions don't always exist, right? But conditional expectation exists under very general conditions. So these, when you do proofs with expectations, those are very fundamental proofs, okay? So you're really proving stuff that's true, okay? As opposed to like doing a little calculation that holds some time, okay? So that's why it's always better to do the proofs with expectations, because it's more fundamental. Okay, and here I think, okay, so that, okay, this is sort of a special case if you compute, I've just did some special cases here. So you can just look at these special cases, read the notes, okay, is the short version of this stuff, okay? So let me see. Okay, now, there's not much time, and I covered what I actually had to cover. I guess I have 2 more minutes. So what else am I going to say? I'm going to give you a high-level view of where we're going next. The next thing we're going to talk about is we're going to talk about Gaussian random vectors. We're going to use Gaussian random vectors a lot. Random vectors and processes. Okay? Gaussian random vectors and processes. Okay, so now the form of the way I'm going to define a Gaussian random vector is by its distribution. Okay, which has the following form right there. It's equations 2.3 in the notes, and it's defined in terms of a covariance matrix. It must be positive definite. I'm going to assume it must be positive definite, not semi-definite, but definite. Okay, so it can't have any zero eigenvalues. Okay, and a mean. So it's parameterized by its covariance and mean. And this form, you're going to, by the end of this class, if you stick with this class, you're going to have this form absolutely drilled into your head, okay? Because we use it a lot in this class. It's really fundamental. And it's, yeah. And then what will happen is that we're going to talk about also various things. We're going to talk about the Bernoulli distribution, which is another random variable that we'll use a lot. And the probability distribution for a Bernoulli random variable looks like this, okay? That's example 2.2 of those. And we're going to talk about sufficient statistics. Sufficient statistics is going to be very important.
25 seconds left.
Yeah, that's the information you're going to use to estimate parameters, okay? So I'm going to switch back to the picture here, the because I always like to go out in style, I guess. Okay, so it was nice having you today, and I'll see you on Friday. Goodbye. We have 3 more seconds. 2, 1, 0. Okay.